Chapter 8 is concerned with confidence intervals, and these are the formulas that we'll be primarily using in Chapter 8. But before we get into these, I'd like to talk about the concept of what we're doing. In Chapter 8, we are continuing to use a sample in order to infer things about the population. And if this gray area represents a population, an infinite population that is, then in order to find out important information about the population, like the mean, the standard deviation, and all of these different types of things, we take samples. And in doing so, each time we take a sample, which may be a small or very large sample, we are just pulling certain pieces of data from that population, and we usually calculate the mean and a standard deviation for the sample. And of course, whatever information we pull from that sample, we use to infer estimates of the mean and the standard deviation of the population. And we infer, that is. So we use this to estimate the mean and standard deviation of the population. And of course, the more samples we take and we compare all of the means of those different samples, the better our estimates become. For instance, we might take another sample, a larger one this time, and this time we would find another mean and standard deviation, and we would use that mean and standard deviation to make inferences, once again, about the mean and standard deviation of the population. We can even have samples that overlap. We might choose a sample that some pieces of data may be repeated between two samples, but we just continue and continue and continue to draw samples and standard deviations and use those to make inferences about the population. And of course, when we take enough samples and calculate the means and standard deviations of those samples, we can actually use that information between these to make a better estimate of what's happening with the population. In fact, the standard deviation that we find between the samples, we did this back in Chapter 8. When we calculate these different means in these different samples, and then we calculate the standard deviation of those means, the standard deviation of the means, that is what we called in our last chapter, Chapter 7, the standard error of the mean, which basically means we calculate numerous sample means and then we calculate the standard deviation between those means. And it's a standard deviation not between items of data, but between sample means. And this is the thought process that we're using in order to we're continuing to work this concept when we do confidence intervals. Now, what is a confidence interval? A population is assumed to have a normal distribution, where the population mean is the center of that distribution and where we have the most data. When we calculate confidence intervals, well, even back here, when we calculate these various sample means, the more means we calculate and the larger the samples are, the closer these means will be to each other, but they will differ. And there is no way for us to know, regardless of how many different samples we take and how many different means we calculate for those samples, we will never know the population mean, especially if, as in this case I said earlier, your population is an infinite population. If we're talking about the number of people who have at some point in their life failed to return a library book, first of all, we would never be able to find all those people. We would never be able to locate all those records. And even if we did try, we would never know if we found them all. And during the time that we're doing all of this, some of those people could potentially pass away. And then new people fail to return a library book. So a population is not necessarily a concrete number because it's a living, breathing entity that's in flux. So that being the case, you will never actually know what the population mean is. Although we can be reasonably sure that it sticks within a certain range of values, that there is some number that represents the mean of the population, and that number is the neighborhood, so to speak, for the population mean. So in this case, when we calculate confidence intervals, we usually calculate 80%. I've seen 85%. One that is in your problem set is 86.9%. %, 95%, and 99% confidence intervals. Now, what does it mean to have an 80% confidence interval? An 80% confidence interval means that when we calculate this range of numbers, we're going to calculate a low value and a high value, a range of numbers which we believe the mean lies between. We don't know exactly where the population mean is, but we can be reasonably sure, in fact we can be 80% sure, that the population mean will lie between these two values. Now, that's only an 80% possibility. It is possible that the mean will not lie between our values. In fact, it is possible that the mean is actually not here at all, that our low and high really aren't centered on the population mean, and it's possible that our low and high are situated here and we just can't be sure of that. And so we hope we can be reasonably sure, that is 80% sure, that the interval is centered on the population mean, but it may not be. Now, the more assuredness that we desire in whether or not our population mean lies in the interval, then the wider the interval will become. Think of it as in learning to shoot a bow and arrow. If we want to be 90% sure that our range of values includes the population mean, and of course, like I said, we cannot be totally sure that the low and the high that we calculate will be centered on the population mean. It's very possible that the population mean is to one side of the interval, and it's also very, very possible that the population mean is not in the interval at all. But it appears that I have destroyed my picture here. I'm going to back up just a bit. This is the way to put it back the way that it was. For a 90% confidence, then we are considering we want to be 90% confidence means that we want to be very sure that our population mean falls within the interval, the low to the high. And if we want to be more sure, if we want more assuredness that the population mean is going to fall in our interval, then that means we have to widen our interval. This is very much the same concept as, for instance, if you were learning to shoot a bow and arrow and you wanted to be sure to hit your target, well, then you make a very large target. You make the target the side of the barn instead of a bullseye on a stand. And so that's basically it. If we want to be more sure, then we give ourselves more space to make sure that the population mean falls into. And so one of the questions I believe that we are asked on the question sets and the test is as you increase the level of confidence, what happens to your range, to your confidence interval? And that is that the confidence interval will widen, which actually takes away from the accuracy and your ability to narrow in on the population mean. And now we'll go back to our formulas. We have been working with z-scores in chapters 6 and 7, and we will continue to work with z-scores. You will find that material very familiar. Now we're going to bring into our toolbox of statistical tests and things, the t-score. And it basically works this way. Whether you're doing confidence intervals or hypothesis testing, which is chapter 9, or any other types of statistical procedures, if your sample is a large sample, now a large sample is defined as a sample with 30 or more units of data. That could be participants, subjects, readings, measurements, whatever your data is composed of. But if we have 30 or more units of data, then we use the z-score. For a sample that has less than 30 units of data, and so that would be anything from 1 to 29, then we use the t-score. And we will talk more about this as we go. What I do want to point out right now is that the sample mean is here, And to that sample mean, we add and subtract this product. Now, this is a z-score, which is associated with your level of confidence. So this is a z-value associated with your confidence level. And this, the standard deviation for the population divided by the square root of the number of the sample, is the standard error of the mean, which we learned to do in Chapter 7. And once we find this product, between the z-score and the standard error of the mean, then that product is added and subtracted to this product is what we call the margin of error. And that will help us in some of our problems in the terminology. Of course, over here for the t-scores, we have the same relationships. This t-score is associated with the confidence level that's given in the problem. And so that is something that we'll have to find, but it is basically provided by the context of the problem. So this is t-value And of course, the standard deviation divided by the square root of n is basically the same thing as the standard error of the mean, except that this standard deviation is for the sample, and that's okay. It's not a big contingency problem. And it is also true that when we do this product here, that is also what we call the margin of error. Now, once we find that margin of error, it is added and subtracted to the sample mean. And that's how we get the low and the high. When we subtract this value, whatever it is, from the sample mean, we'll get the low end of our range. And when we take this product and add it to our sample mean, we'll have the high end. Our first example problem is one in which we are asked to find the 86.9%, 95%, and 99% confidence intervals. The problems that you are assigned in the question sets and tests do not ask you to do all three at the same time, but I thought that I could cover more ground by doing all three in a single example problem. Now, the first thing that we will want to look at in a problem where we're asked to calculate or construct a confidence interval is the n value, because that's going to determine whether or not we calculate a t-score or a z-score for these confidence intervals. And the problem won't always specify. In this particular example, it does say find the z-values associated with, but it does not always specify. So we know that our sample is 256. So we're going to go ahead and write down our given information. N is 256 students. Since this is a large sample, we can be sure that we're supposed to be working with z-values. Now, we have other information. It says it was determined that students in the sample spend an average of 14 hours watching television, that is. It appears that part of my sentence was chopped off. So we also know that our x bar is 14. And the standard deviation is 3.2 hours per week for all freshman students. Now, all freshman college students indicates a population standard deviation, which is 3.2. And of course, this is our population notation here, so that is the correct statistic for us to use. Now, A says, find the z-values associated with the 86.9%, 95%, and 99% confidence levels. Now, I need to explain where those things come from. It is true that there is a page in the text that gives a brief chart of some common confidence levels. It is on page 319 at the top of the page. But at the same time, it does not give all the confidence levels that one may be asked. So let's talk about how to calculate a confidence, a z-value for a confidence level. This is a throwback to chapter 5 and 6 where we started working with z-scores. This is what we are doing. We are basically looking at an 86.9% area that is centered on the theoretical population mean. That would be the mean that is right there in the center of the population. And we consider this 86.9%, like I said, to be right in the center. And as such, if it is positioned directly in the center, then that means that it is symmetric on the population mean, which means that these z-scores that are to the left and the right of the mean are opposites of one another. We have a z-score here and a z-score there. And here is 86.9% of the area under the curve. Now, in order to find this z-score, we are going to want to know what this area is. Since the z-charts are set up in such a way as to only show left areas, then this is the area that we're concerned with. So in order to find the size of this area, we take 100%, subtract the 86.9%, and divide by 2, since of course this is only half of the remaining area under the curve. 100 minus 86.9 is 13.1% divided by 2. And then, of course, that will be 6.55%, which is also equal to 0.0655. The area in this section is 6.55%, or as a decimal, 0.0655. This is the value we will look up in our chart. So we start looking in the body of the chart for the 0.0655, and we find it right in here. And so we see that the z value that is associated with this 0.0655 is negative 1.51. And so therefore we know that the z-score here is negative 1.51. Since this area is symmetric on the mean, this z-score is 1.51. Now we'll only need to use the positive value in our calculations. So this is the way that we go about identifying that z if the z has not been previously given. And in fact, I would probably make myself a chart because you really don't want to look them up repeatedly. And so confidence and z. For an 86.9% confidence level, the z-score is 1.51. And of course, in the chart that we see on page 319, we see that for a 90%, it is 1.645. For a 95%, 1.960. And for a 99%, 2.576. So we have our answers for A. For A, the 86.9% is 1.51. The 95% is 1.96. And of course the 99% is 2.576. B. B asks us to determine the standard error of the mean for the given standard deviation. Now, Keep in mind that all of these z values that we've just found are basically our finding of this z-score. And of course, we're really working 3 different problems in one, so each one of these will be used in a separate calculation. The standard error of the mean is this portion of the problem. So now we're just finding the standard error of the mean, which is basically what we learned back in Chapter 7. It's the standard deviation for the population divided by the square root of n. So the standard deviation for the population is 3.2. And we are dividing that by the square root of 256. And the square root of 256 is 16. So it's 3.2 divided by 16, which should be 0. So this value, 0.2, will be the standard error of the mean each time we do the calculations. Part C. Construct the 86.9, 95%, and 99% confidence intervals estimates for the average number of hours that all college freshmen spend watching TV per week. So in Part C, I'm going to go up to this part, and we'll do the 86.9% first. We are essentially going to take our sample mean, and we are going to add and subtract the z-score for 86.9 times the standard error of the mean. So our sample mean is 14. And we are going to add and subtract the z-score for that, 86.9%, which is 1.51, times 0.2. And of course, this will be, I believe, 0.302. And it's going to be time for me to get my calculator, just to be sure. Now, at this point, we're going to add and subtract the 0.302 to 14. So we'll say 14 minus, and we can type in 0.302, and it's 13.698. And now we add the 0.302 to 14. 14.302. And that is our confidence interval, the 86.9 confidence interval for this scenario. We will do exactly the same thing for the 90 and the 95% or the 95 and the 99%. The only difference in what we do this time will be that instead of using 1.51 as our z-value, we'll be using for the 95 1.96. And so it will be 14 plus or minus 0.392, and we can subtract the 0.392, $13.608. And of course, it always seems the adding is easier than the subtracting. And we will continue this same process to do the 99% confidence interval. The only difference is that instead of using 1.96 or 1.51, we will be using the 2.576. If you're using a graphing calculator, a TI brand, you can press second negative sign, which brings up the command ANS, which is basically the last answer that was left in the calculator. So it's 13.4848. And then, of course, we can add the 0.5152 to the 14.5152, which we may on this one round it to the third decimal place. So our answers are for 86.9%, this interval, we have the 13.608 to 14.392, and of course on this one we have 13.485 to 14.515. And notice that if we were to subtract the high minus the low, or basically if we were to double this error, this actually is called, as I mentioned before in the opening, this is called the margin of error. If you double your margin of error, it will be the distance between the high and the low. And so the range on these, this is a side note, here is 0.604. The range on this one is 0.784, and that is an 8. And the range on this one is double the 0.515, which is 1.030. And of course, once again, this represents the size of the range between the two values. Notice that as our confidence level increases, for instance, this was the 86.9, this was the 95, and this was the 99. As our confidence level increases, so does the width of our range. And that is because the more confident we want to be, the more room we have to give ourselves to trap the population mean within our range. And so that finishes up parts A, B, and C of this problem. Now for part D, it says, suppose that the sample mean, the size of the sample was 25. Now, that is going to require t values. And I'm going to do a problem for t values in the next example, and then we can come back and revisit part D. In our second example, we are calculating a confidence interval using t-values. And like I mentioned in the earlier example with z-values, your problem will not always specify whether it should be z or t, but you can tell by the sample size. Here it says a sample of 16, which indicates that your sample size is less than 30. So since our n value is a value less than 30, we know that we're going to be working with t values instead of z. We can also pick other information from this part of the problem. The average age was 22.5. That is the average age in the sample. And it has a standard deviation of 5 years. And of course that is a sample standard deviation because it did not say of all consumers. It just said the sample has a mean of 22.5 and a standard deviation of 5. It says A, find the t-values associated with 80% and 95% confidence. Now, in this case, we're still going to be looking at the normal curve, and I'm just going to briefly draw. My freehand bell curves are not very good, but for 80 and 95%, we are still assuming that there is a normal distribution. We are still centering our area here on the mean. We are still considering that this 80% area is centered on the population mean. We are still looking for a z-score here on both sides of the mean, and all of this remains consistent. The only difference is instead of a z-score or a z-value, we're looking for a t-score. And of course 80% of the area is in this portion. To find the amount of area that should be here to the left side of this t-score, we still do the 100% minus 80% divided by 2. And of course that's going to be 20% divided by 2, which is 10%. And 10% as a decimal is 0.100. And that is the 10% here in the tail. In order to find this t-score, we're going to have to go to a t-chart. The t-charts are located in our textbook in the appendices at the back of the book, but not in the front covers. This is what our t-chart looks like, and we have something new in our t-chart, and that is degrees of freedom. Whenever we are doing t-scores, we work with degrees of freedom, and the degrees of freedom is always equal to the sample size minus 1. So in this case, since our sample size is 16, it's 16 minus 1, so the degrees of freedom is 15. This means that we will be looking I'm going to take a picture here. This means we will be looking on the line with 15 degrees of freedom. Now, the area in our upper tail. The area in both tails is the same, whether it's the upper tail or the lower tail. And so in this case, the area in the upper tail is 10% or 0.10. So when we look at our columns, we're clearly going to be in this column, and so the score that we're going to be using is the 1.341, and that would be of course for the 80%, so we might specify that. Part A, for the 80%, it's going to be 1.341. Now, for the 95%, we can go back to our chart, and it's still 15 degrees of freedom, but basically the area in the upper tail is going to be half of 100 minus the confidence level you are seeking. So if we're seeking 95%, then half of 100 minus 95 is 0.025. And that means that for our second confidence interval, we're going to be using the 2.131. For part B, determine the standard error of the mean for the given standard deviation. In this case, we're going to be using the sample mean, and so S divided by the square root of n is the 5 divided by the square root of 16. So it's 5 over 4, which is 1.25. And of course, the formula we'll be using is the sample mean plus or minus the t-score times the standard deviation divided by the square root of n. And essentially on these problems, what we're doing is in part A, we're figuring out what the t-scores are. In part B, we're calculating the standard deviation divided by the square root of n. And in part C, we're just putting it all into this formula. So, for part D, 80% confidence interval for the average age of all, we're doing the 95% first on part C. So, we will use the 2.31 as the t-score. We'll use the S divided by the square root of n, which is 1.25. And we will add and subtract that to our sample mean, which is 22.5. And we can round this to 2.664. And then of course we can add that to our same value. And I'm going to pull the last thing I typed in by pressing second enter, and then I can just arrow over and change that subtraction to addition. And it's 25.164. And that is our part C. D, do the 80% confidence interval. So we're doing the exact same thing, except that this time we are using the t-score of 1.341. So it's the 22.5 plus or minus 1.341 times 1.25. $1.676 is our margin of error. Change that to addition, and we have the 24.176. On Part E, discuss why the 95% and 80% confidence intervals are different. Now, once again, we're talking about why the more confidence we desire in our interval, the wider our interval has to be. And for instance, here, let's revisit a couple of things. When we multiply the t-value by this standard error, we get this value, which is called, usually, this value is the margin of error. That margin of error is added to the 22.5 and subtracted from the 22.5. So essentially, the difference between the low end of our interval and the high end of our interval is double the 2.664. 2 times 2.664 is a value larger than 5. $5.328. And of course here our range is double the 1.676. Which is some value larger than 3 but less than 4. Now, this was the 80% confidence. This was the 95% confidence interval. With more confidence, we have to widen the range so that we can be sure that our target, which is the population mean, will fall within that range. With less confidence, our range is much narrower and is much more decisive. The only thing about a lower degree of confidence is we cannot be as sure that the population mean will fall in that narrow window of values. And so that is essentially the what question E is asking you to describe. With higher confidence, we have a wider interval. With lower confidence, we have a narrower interval. And that would answer that question. And I was going to make sure before we left this that I also pointed out that this is a margin of error for the 80%. And that wraps up our confidence intervals using t-values. Back to our first example problem, we were going to come back and answer part D. D is here. And we have the same problem except that we are to change our sample size to 25 students and provide a 95% confidence interval. And so we're going to make a new page. I think we'll copy this. And we're just looking at, as I mentioned, part D. So for a 95% confidence interval when n is equal to 25. Since this n value is less than 30, we'll be using a t-score. And that means that we'll take the sample mean, add and subtract a standard error, which is calculated with a t-score, multiplied by the standard deviation divided by the square root of n. And so our sample mean was 14. We need to find the t-score that corresponds to 95%, and so that is going to be I'm going to make a copy simply so that we can mark on our values. All right, so degrees of freedom. We have to have degrees of freedom in order to read a t-chart. So degrees of freedom is n minus 1. Since we have 25 in our sample, our degrees of freedom is 24. Which is here. And since our area is 95%, the area in the tail will be half of 100% minus 95%, or half of 5%. So we're looking at the 2.064. Our t sub alpha over 2 is 2.064. And we can put that here. To calculate the standard error, we would use the same standard deviation we were given, which is the 3.2. And divide by the square root of 25. So we're going to have 3.2 divided by 5, which is somewhere in the neighborhood of 0.6. .64 actually. And that's what we'll multiply by the 2.064. And we can add and subtract that to 14. And we know that that's going to be 12.68 to 15.32. And that would be our confidence interval given a sample of 25 students. I was simply looking at our previous confidence intervals to see how they compare. But it's actually, we would be comparing it to this one since this was a 95% confidence interval as well. And we can see that the one with the sample of 25 gave us 12.68 to 15.32, something like that. So a 95% confidence interval with a z-score is going to have a smaller range. That means it's going to be wrapped a little more tightly than a t-score or a confidence interval on the same let percentage of confidence but used with a t-score with a small sample. Small sample is not as reliable as a large sample, and so this is going to be wider. And that wraps up all of that particular problem.